In this session we're going to be introducing functions. A function is a set of ordered pairs in which to each first component, or input, there corresponds exactly one second component, or output. So when we have an input, which would be like an x, we get an output, which is an f of x. Now in the past, we've used y as an output. So when we've had y equals, let's say, 2x plus 1, if x is my input, and let's say I input a 2, I get y, the output, would be equal to 5. So I'd have the relation 2, 5. But now, let's say f of x equals 2x plus 1. Now if I want to find f of 2, 2 being x, which is my input, I get that to be equal to 2 times 2 plus 1. So f of 2 equals 5. So still, with this notation, if I still input a 2, I still get an output of 5. Hence the relation remains 2, 5. So if you haven't seen this function notation before, it's very, very similar to just using a y. Now, graphically, in order to be a function, it has to pass a vertical line test. So if I have a series of graphs, let's say one looks like this, which is a quadratic equation. One looks like this, which is linear. And then let's say we have one that looks like this. Okay? Now what is a function? So the vertical line test means that anywhere where we can put a vertical line, let's say like here, or here, or here, or here, anywhere on the graph, we only intercept our line, or our actual graph, once. If that is true, then it passes the vertical line test and it is a function. So as you can see, this one, any vertical line placed on there will only hit the graph once. Same with here. If we draw as many vertical lines as we want, it's only going to hit the graph once. This is a function. But now when we go down here, we're hitting it once, and then boom, all of a sudden 3 times. But all we need it to do is hit that more than one time once. This is not a function. So let's play around a little bit with these. Let's say that the function f is equal to 4x plus 3. And let's say I want you to find f of 3. To find f of 3 means that I just want you to put a 3 in place of x and then find out what you get. So if we do that here, we'll have 4, then there's our x, so instead of an x we'll put a 3 plus 3. Well, what is 4 times 3? It's 12, plus another 3 is 15. So f of 3 equals 15. Or we could say that it's an ordered pair, 3, 15. Now let's say we have g of m is equal to m squared minus 4. This time the name of the function is g, and the input variable is an m. So if I want you to find g of 3, that means I'm going to put a 3 everywhere that I see an m. So there's an m, I'll put a 3, throw in my parentheses first, squared minus 4. So g of 3 equals 5. It'd be 9 minus 4. So 3, 5. Now let's get just a little bit more complicated. Let's say f of x equals 7x minus 3. Not so bad so far. But let's say I want you to find f of r plus 1. Now this means everywhere that I see an x, I'm going to put an r plus 1. So now f of r plus 1 equals 7. I see an x, r plus 1 instead, minus 3. So this equals, using the distributive property, 7r plus 7 minus 3. And for a final answer, f of r plus 1 equals 7r plus 4. Now if I want to graph functions, it's essentially the same way that we've graphed before. If I want to graph y equals negative x minus 4, I'd first find my y-intercept, which is negative 4, plot that point. My slope is negative 1, so I go up 1 to left 1, and there's my line through those 2 points. Now if I want to find f of x equal to negative x minus 4, over here we had a y-axis and an x-axis, but here this is going to be my f of x axis and my x-axis. So we're just replacing an f of x for y. It's going to be the same thing to graph this. Find my y-intercept of negative 4, use my slope of negative 1 to go up 1 to the left 1. It's the exact same line. So graphing things in the form y equals mx plus b or f of x equals mx plus b, I'm going to get the same graph. So if I want to graph, let's say f of x equals 1/2 x plus 3. That means I'm going to have a y-intercept of 3. Then to find the next point, I'm going to go up 1 to the right 2. And then I'm going to draw a line between those 2 points. Here's my line. Now we need to go over what's called the domain and range of a function. The domain is the set of first components or the set of inputs, or kind of you could think of it as, and don't confuse it with this range, but the domain is a range of all the possible inputs. So you have to ask yourself, is there a value that you can plug in for x where you will not get an answer or an output of f of x? And the answer is no. You can take any number, multiply it by 1/2, and then add 3, and you'll still get an output. So the domain for this function is going to be all real numbers. Or if you wrote that in interval notation, which we've covered before, it would be negative infinity to infinity. Now the range is the range of outputs, or the set of the second components. So if by looking at the graph, this is probably the easier way, by putting any horizontal line in anywhere, starting actually from negative infinity to infinity. Now remember, these lines go out forever. So no matter where you put a horizontal line, negative infinity all the way to infinity, you're still hitting this original line that we had. So the range is going to be from negative infinity to infinity. Now you can do the same thing for the domain, and this can be sort of a good way, kind of an easy way to determine domain and range. So for the domain, if you start way out at negative infinity, and let's make this line a little bigger, or maybe let it stick out. So let's say there's our line, and remember those arrows signify that it's going out in those directions forever. If I want to find the domain of this, I'm going to take a vertical line at negative infinity. Am I going to hit the graph, the blue line? The answer is yes. As I take that vertical line and I move it, and I keep putting a vertical line, as I'm working my way to positive infinity, do I hit that blue line everywhere? The answer is yes, I do. So the domain is negative infinity to infinity, since I hit the line everywhere. And then for the range, instead of doing vertical lines, now I'm going to go to negative infinity with the horizontal line. Now, am I going to hit the blue line? And the answer is yes, because that blue one goes down forever. Now, as I'm working my horizontal line up, am I still hitting the blue line everywhere? The answer is yes, I am. So the domain, or the range, is from negative infinity to infinity. But now let's say we've got something like this. This is the graph of y equals x squared. Now if we take a look at the domain. So the domain, remember we're taking a line from negative infinity to infinity. We're always hitting this graph. So the domain is all real numbers, or from negative infinity to infinity. And again, the other way to look at it is, can you plug a number in for x that you can't square? The answer is no, you can square any number. But if we've got this now, which is still our same graph, y equals x squared, but then now we're looking for the range. Now we're putting this line down here from negative infinity to infinity. We're working this horizontal line upward. Are we hitting the graph? No, we're not. So the range is not down here. As we move this horizontal line up, once we get to y equals 0, we finally hit right here the bottom of that function. And now from 0 to positive infinity, we're hitting the graph. So the domain here is going to be from 0 to positive infinity. Now anytime we have infinity, we write parentheses. But now we're including the 0, so we're going to use a bracket. So this would be, this is the range. The range is the horizontal line, the domain is the vertical line. The range here is from 0 to infinity. We just did the domain previously.